Pepsi ran a promotion contest for their 20-ounce bottles of soda. Some of the caps said, please try again. Others said, you're a winner. Pepsi advertised the promotion with a slogan of 1 in 6 will win a prize. All right, so let's pretend we take a stats class and we wonder if this is true. Here we go. So 30 students go to the store and buy a Pepsi bottle. 2 of the 30 end up winning. So the question is, how many winners would you expect to get out of 30? Yeah, 5. Why? How'd you get 5? Okay, so she took 30 students. The probability is 1 out of 6, right? 30 divided by 6, so we expect 5 winners out of 30. That's the expected. In probability, instead of we saying average, we say the expected count. Okay, but it's the average, and that's how you get there. All right, does this give us convincing evidence that the company's 1 in 6 claim is inaccurate? Let's design a simulation to help this question. So what we're saying is, okay, we only got 5 winners, we would expect to get 5 and we only got 2, right? So is their claim untrue, or did we just get unlucky? See what I'm saying? That's where it's saying, do we have convincing evidence? Because it could just be an unlucky draw, right? Or they're just straight up lying. We don't know. So what can we use to model a 1 in 6 probability? What chance process out there has a built-in 1 out of 6 probability? A die, right? Rolling a die. All right. Now, before we roll a die a bunch of times, we have to assign some outcomes, all right? What outcomes on the die are losers? Which ones are winners? So how's that going to work? 1 out of the 6 has to be a winner and the rest are losers, right? Which number do we want to make the winner? 6? Sure. So number 6, if we get number 6, that means it's a win. If we get 1 through 5, that means we lost, right? Now we're going to use, on your phones or wherever, you're going to use random.org/dice. Yes, there is a die. And I believe I have a die up here. Nope. Yes, I do. Lovely. Okay, so we have a die. You're going to need to do this too. But I'm going to simulate rolling the die 30 times. And you need to keep track how many times out of your 30 did you win. Hello? It's okay. I do. You need her? Yes, ma'am. Will do. Bye. You know what it is? Okay. You know where to go?
Yeah.
Okay. Yeah. Okay. So I'm gonna roll mine. Okay. I can only do it 6 times. Okay, so I get 1. Out of 6, we got 0. 2. I got 1. 0. Okay. So out of my 30 trials, I got 4. How many did you get?
4.
You got 4 also? Did you use the random.org thing? Yeah? Okay, great. So you have a number of wins on your trial, right? Let's do the simulation one more time. How many win the prize this time? Okay? More trials, the better, right? One, 0, 1, 2. I got 4 again also. How many times did you win the prize the second time? I got 4 again. All right. So what we're going to do is create a dot plot with all of our numbers of wins. Everybody got 2 trials done? Yeah? Did you? Sweet. Okay. So like for me, I got 2 4s. So I'm just going to put dots, 2 4s or 2 dots on the 4. So we're going to go around the room and you're going to give us your 2 numbers. And we're going to see where do the wins line up. Everybody got your 2 numbers? Okay, John, what'd you get?
I got a 3 and a 2.
A 3 and a 2. Elijah?
I got a 3 and a 5.
Okay, 3 and 5. David, what'd you get?
I got 3 and 5.
You also got 3 and 5? All right, Lucas? 3 and 2. Riley? She's a lucky gal. 7 and 8. Olivia?
3 and 4.
3 and 4. MJ?
5 and 5.
Cheyenne? 2 and 5. And Kinley?
3 and 5.
All right. Ava?
3 and 4.
3 and 4. Julie?
4 and 6.
4 and 6. See, Trent? 3 and 4. Zuhair? 6 and what? 7. Okay. Owen?
10 and 5.
5 and 5?
10.
You got 10 for real? Dude, 10 and 5. You're an outlier, dude. Okay. Julius?
4 and 3.
4 and 2. Hannah?
4 and
4, 4. Michelle?
6 and 7.
And last but not least, Katie?
8 and 6.
8. My goodness. Okay. 8 and 6. All right. So how many trials do we have all together here? Let's count these guys up. 1, 2. I got 38. Did y'all get 38? Somebody else count? Okay. I got a total of 38. What percent of the time did we get 2 or fewer prizes? So we look at our dot plot. 2 or fewer. Fewer would be this direction, right? Left. So that counts up 4 times. So 4 out of 38. All right. I don't know what percent that is. Do you?
10.5.
Is it? Thank you. 10.5%. There we go. Okay. So then the question is, does it seem plausible that the company is telling the truth, but the class just got unlucky?
Yeah.
We just had an unlucky day. Looking at the outcomes, are there outcomes that are greater than what you think? Yeah, there are. So it's not impossible to win, right? Owen proved them wrong, right? It's not impossible. It's just saying, like, in this scenario, in this simulation, is what we call it, only 10% of the time did we get something lower than 2. Which is not impossible, and it's not that surprising either, right? Okay, so does it seem plausible the company's telling the truth, just got unlucky? Or do we have convincing evidence that Pepsi's lying? Okay, so here's the criteria. Since 10.5% chance is not considered unusual. I should say unusual given random chance. The class just got unlucky. Okay? Class just got unlucky. That's all it says. So then the question comes up. Well, then, what is considered unusual, right? So just food for thought. It's not a big deal right now, but what is unusual is less than 5%. If you ended up with a probability that's less than 5% of the time, we consider that unusual. And when you say unusual in statistics, that translates to convincing evidence of whatever it is we're testing, okay? So the magic line is 5% or lower. So 10%, not unusual. Is that all right? So what we've done is take a chance event and simulate it to get the actual probability, all right? So in this trial, it said 1 out of 6 chance, right? So 1 out of 6 chance translates to like 16% probability of winning, right? But is that what our trial said? No. Our trial came out with a higher chance of winning, didn't it? Than 16%? So 1 in chance. Didn't need to do that. So you would use our results from your dot plot that you create when you do a simulation or whatever results you have, use that to use the probability, not the one that they give you like here. We would use the results of this to predict it. We'll do an example, don't worry. That seems weird. I know, it seems very strange because it's like, why wouldn't I just use that? Well, because they want it based on the simulation, okay? So let's look at this. So simulation is the imitation of a chance behavior based on a model. I believe it accurately reflects the simulation. Let me look it up. Yeah, accurately reflects the model. Accurately reflects the situation. What other chance random devices do we have that we can use to model random situations? Coin, yep, flip a coin. A die would be 1 out of 6, right? Situation, flipping a coin would be a 1 out of 2 probability. What other random tools do we have? Huh? Hat method? Yeah. We have the hat method. We have a random number generator. These are a little more customizable, right? So if you have something that's a weird, like 7% chance, you can make it work using that. You know, if it's 7% chance, you would use like a random number generator, 1 to 10. And if it lands like on you would identify like 1 to 7 would be a winner, and 8, 9, 10 would be losers, right? You would set up the numbers to reflect that probability. That's all you got to do, all right? So in this simulation process, now you're not going to like this because this is the wordy part of Chapter 5, and this is the end of the wordy part of Chapter 5. So stay tuned, it's not bad. If you're asked to set up a simulation, this is kind of what you want to do first. You want to first describe one trial. So this is that random thing that we did in Chapter 4, you know. Set up the trial like we just did. Like we said, when we roll the die, a number 6 is a winner, but 1 to 5 is a lose, right? So we roll the die and we use that outcome. We randomize it, we select, and then we count how many. Now you have to set up in there how many times you're going to do it. Like in our example, we did 30 times, right? How do you know when to stop the trial? Well, we stopped after 30 trials, or we stopped after whatever the question predicts it should be. Okay, so, but you perform many trials, but it's important that you explain in your description when you're going to stop. Okay, so you describe it, perform it however many times, and Then you use the results from your simulation to answer the question. What do I mean by that? Well, what I mean is this. So I'm going to flip back for a second just to the first page to remind you. Let's do this. Okay, people have wondered if the Wheel of Fortune wheel is fair. If it is fair, the bankrupt result should only occur with the probability of 1 out of 9. To test the wheel, Pat Sajak observed a random sample of 50 spins and found that bankrupt was spun 10 times out of 50. Is this convincing evidence that the bankrupt comes up more than it should? So, describe how we would carry out a simulation to estimate the probability that in a fair wheel, the bankrupt comes up 10 or more times. All right, so we need to set it up to reflect the correct probability. What does it say the correct probability of a bankrupt is? 1 out of 9. Okay, so 1 out of 9 doesn't work with a die, does it? Because it's only 6 sides. It doesn't work with flipping a coin. So this is an example of where you would use like a random number generator to help you. All right, so we're going to assign the numbers, whether it's bankrupt or not bankrupt, right? All we care about on the wheel is whether it lands on bankrupt or not. How many bankrupts out of 9 are there? 1, based on that probability, right? So I would say it like this. I would say label number 1 as bankrupt, and then 2 through 9 as not bankrupt. So you're identifying the 2 outcomes you're considering. Then, okay, so that would be my first step, label, right? Then I would use a random number generator to generate numbers between 1 and 9. I don't want it to go 1 to 100. I just want 1 to 9. Now, does it matter if I end up with repeated numbers? In this case, it doesn't matter, right? It does not matter. We're just looking at outcomes of spinning the wheel. Then I would count the number of ones. Oops. Generated. I can't do it just once, right? I'd probably say repeat until 50 spins are simulated. So maybe you could say that was your number 3. Repeat it till 50 spins are simulated, and then go back and count how many times did you get bankrupt out of 50, right? So this is how you do the simulation. So now this dot plot is saying, and this is how it'll be given to you in a question too. They're not going to actually make you do the simulation usually. So this dot plot, it says it displays the results of 100 trials of 50 spins in a fair wheel. Okay, so they've done our little suggested simulation 100 times, and these numbers, notice what it says, the simulated count of bankrupts out of 50. All right, so make sure you register what that means, okay? This is the number of bankrupts out of 50 in one trial. Each dot represents how many bankrupts did you get out of 50 in one trial. So this is where technology is our best friend, because it did 100 trials for us instantaneously. All right? So I kind of just did letter B. What does one dot above the 12 indicate? It indicates that in one trial of 50 spins, 12 bankrupts were landed on? All right, so let's go and see. What did they claim the probability of landing on bankrupt is? 1 out of 9. Or let's look at the trial, with the one that brought up the question right here. It says, Pat Sajak observed out of 50 that it was spun 10 times, right? So we're trying to figure out what is the probability of getting 10 bankrupts or more out of 50. That's what we're concerned about here. So look at our dot plot. How many times did it go 10 or more? Only 4, right? Only 4. So is this unusual? It's 4 out of how many? How many dots are on there? 100. It's 4 out of 100, which is easy math, right? 4% chance. That's lower than 5, so we would consider it to be unusual. Okay, so 4 out of 100 translates to 4%. All right, because it's under 5%, we consider that unusual. So we're using that as our barometer on, is it sketchy? Is the wheel unfair, or is it just random chance that he got that many? Well, we consider it unusual because it's so low. So the way I would write my conclusion, I would say, assuming the wheel is fair. Okay? Assuming that the wheel is fair and not weighted, there is about a 4% chance of getting ten or more bankrupts out of 50. There's about a 4% chance of getting 10 or more bankrupts out of 50. So then I gotta zoom in and write really small here. So I would say, since 4% is less than 5%, this is convincing evidence of an unfair wheel. It's convincing evidence of an unfair wheel. Is that all right? Convincing evidence of unfair wheel. Why did we have to do 100 trials? Do you know why? What'd you say, Hannah? Replication. Why is replication important? Why do we need it in this case?
So we can assume cause and effect.
You're thinking about experiment. Well, because Pat Sajak having one bad spin or bad round of 50 spins, does that predict all of it? Is that enough for law of large numbers? No, absolutely not. So we have to do the simulation to see what does this really turn out to be in the long run. All right. So you will see some simulation questions, but I guarantee it's not a lot. Yes, they're tedious when you have to write out the steps. A lot of times you don't necessarily have to write the steps, but you just got to read the question. And sometimes you're just given this, where they did the simulation for you, and your job is just to find the probability from it and draw a conclusion. All right? So you'll have some practice in this chapter of doing just that. But this is the wordiest part of chapter 5. All right? So we'll put it at the front end since you're used to doing the wordy stuff.